This is Precalculus, section 1.5, Analyzing Graphs of Functions. So in our last section, we focused primarily on algebraic and numerical functions, and we learned how to identify if a numeric or algebraic relation is a function, and we also started talking about domain and range of these types of functions. And in this section, we're going to focus almost exclusively on graphical representations of functions, and we're going to learn to pick out some important information from these. So the learning goal for this section is to determine the domain and range of functions and determine the intervals in which a function is increasing or decreasing. And the way we're going to achieve this goal is by 1. Determining whether graphs represent functions. Next, we're going to find the domain and range of graphs of functions, as well as increasing and decreasing intervals for these functions. So the first thing we're going to look at today is determining whether a graph represents a function. And the way we're going to do that is by using what's known as the vertical line test. Now, the reason this simple test works is because a graph is only a function if and only if no vertical line intersects that graph at more than one point. And so to perform this test, all you have to do is draw a parallel line to the y-axis, so we're talking about a vertical line. And if this line intersects your graph at more than one spot, then this graph does not represent a function. And the reason this works relates back to what we talked about last section, where we established that each x can only have one output or one y value. So let's take a look at these four graphs and try out the vertical line test. So starting with this graph on the left, again, all you have to do is draw a vertical line through your graph. And if it intersects at more than one point, your graph is not a function. And so this vertical line I just drew intersects our graph at two different points. It intersects right here and it intersects right here. That means that this x value has two corresponding y values. Therefore, this is not a function. If we look at our second equation of a circle here, we go ahead and draw a vertical line. Once again, we can see that this vertical line intersects our graph at 2 points, so we can then again conclude that the equation of a circle is not a function. For our next graph, we can go ahead and draw a vertical line, and here you can see it only intersects it at 1 point. So let's go ahead and draw another one. And we can make a couple more throughout here, but it's pretty clear that wherever we draw a vertical line, it's only ever going to touch your graph at 1 point. And so any vertical line that we draw on this graph is only going to intersect the graph at 1 point. And so yes, this one is a function. And for this last one, we have a piecewise function, and we can do the same thing by performing the vertical line test. Wherever we're going through, notice that one endpoint is open and the other one's closed, so we're only intersecting still at 1 point. So this one is in fact a function as well. And so as you can see, testing graphs to see if they're functions or not is a fairly straightforward process by just using the vertical line test. So for this next part, we're going to work on determining the domain and range of functions. As we established last time, the domain is essentially all possible inputs of a function, or all possible x values. And the range is all possible outputs, so all possible y's. So let's take a look at this graph. Now this graph doesn't represent any specific function. It's just a great example to illustrate how to obtain the domain and range from a graph. And so to determine our domain, again, we want to look at the x values. So the first thing we want to do is figure out what is our smallest x value. So I got to look at this point that is the leftmost point of our graph, and that would be the coordinate -3, 0. And so our smallest x value is just -3. Likewise, if I look at our rightmost point in this graph, we have the point 1, -4. And so our largest x value is 1. And so since this graph is a smooth, continuous curve, we can say that we want all x values between -3 and 1, and we can initially just express that verbally. However, we want to go ahead and translate that into an inequality, which is the form we'll be using the most for these types of problems. And so we're saying x values between -3 and 1, and notice that the point -3, 0 is an open point, so we're not actually going to include -3. But for our point 1, -4, it is a filled in dot, filled in endpoint, so we're going to do less than or equal to. Now looking at part B, we're asked to determine the range of the equation. And so recall that the range is just the set of all possible output values or all possible y values of the equation. And so we're looking for y values now. And a good way to start is just by finding the smallest y values. And there's actually two of them that are at the same y value. We have the point that we had already used, 1, negative 4. But we could also use negative 2.5, negative 4. It doesn't matter which one you look at because they're both at y is equal to negative 4. Once you find your smallest, however, once again find your biggest y value, and here it doesn't matter which of the two you choose. You can either choose this point or the point negative 3, 0. They are both at y equals 0. And so again, we can describe this verbally as all y values between negative 4 and 0. And you want to make sure you always list out your small number first. That'll help you write out your inequality. And so when we write down the inequality, we're looking for y values between negative 4 and 0. And in this case, both of our endpoints are included. So we're going to use less than or equal to. So let's go ahead and look at a couple examples where we don't necessarily have endpoints like our previous one. And we are asked to find both the domain and range for each one of these equations. So if I look at my first one, for our domain, although it may not seem like it from just this portion of the graph that we can see, the arrows mean it keeps growing not just up, but also this parabola grows to the sides. So actually for our domain, one way we can represent this, that it keeps going on forever in both directions, is just all x values between infinity and negative infinity. And notice I purposely didn't do less than or equal to because in reality you can never be equal to infinity. And so since you can be any number between negative infinity and infinity, really all that means is that you can be any real numbers. So all real numbers work for your domain. So now if we look for the range of this function, we're looking for our y values. And we do actually have a smallest y value, and it would be at this point 1, negative 4. Notice, however, again, we have the arrows on the other ends. That means it keeps growing forever. It keeps going on to infinity. So for our range, we can simply say that it is any y value greater than or equal to 4, but less than infinity. Likewise, you could just say any y value greater than or equal to negative 4, which means the exact same thing. So therefore, for this parabola, we have a domain of all real numbers, and we have a range of any y value greater than or equal to 4. And so for our next graph, we have an example of a square root graph where we see something similar, but for our domain, again, we're looking for our x values, and in this case, we do have a smallest x value, which would be at the point negative 4, 0. And as you can see on the other side of our graph, we have an arrow, so that means it keeps going on forever. So again, we can say that our domain is all x values between negative 4 and infinity, where the negative 4 is inclusive and the infinity is exclusive. And just like before, we can summarize this by just saying any x value greater than or equal to negative 4. And so for our range, that same point, negative 4, 0, is also showing us our smallest y value. So y is greater than or equal to 0. And also notice that our graph is not only growing infinitely to the sides, it's also growing upward, even though it might not be at a very high rate. However, our y value is going all the way to infinity. So we can say it's just all y values greater than or equal to 0. So now that we know how to determine domain and range of functions, let's start talking about different pieces of our equations and our graphs. Specifically, we're going to be looking for when our functions are increasing, decreasing, or constant. Now, the notation you see here might look a little bit confusing. However, all this means is for increasing, as we are moving from left to right, if our y values are getting bigger, then our graph is increasing. Likewise, as we're going from left to right, if our y values are getting smaller, then that just means we are decreasing. And then the last one once again says if we're going from left to right, if our y values stay the same, then we're staying leveled or we're staying constant. So let's take a look at the graph on the right. Now, before we start analyzing too much, it's useful to kind of just pinpoint some key points on this graph. And these key points are called relative maximum or relative minimum. And that's essentially just either the bottom of this valley or the top of the hill, if you would like to think about it that way. But then you can start analyzing this equation a little bit more and realize there's a few things going on. So you always start by looking from your left side and building your way through the equation to the right. If you notice from the left, our y values are getting smaller up until we reach the point -1, -2. And so similar to what we did with domain, we're going to be looking for our x values here. And here we can say that we are decreasing from -infinity to -1. And once again, the reason we start at -infinity is because of the arrows of our graph, and we are going downhill, if you'd like to think about it that way, up until we get to x is equal to -1. Now, from x is equal to -1 to x equal +1, our y values are getting bigger. So again, if you like to think about it this way, you are going uphill. So therefore, from the interval -1 to +1, we are increasing. And so for the last portion of our graph, from x is equal to 1 all the way to infinity, we are decreasing again. And so we have a second decreasing interval from 1 to infinity. And so if we look at one more quick example here, again, start by just identifying some of these relative minimum and maximum. So here we got the point -1.5, -4. We have our point 0, 0, and then we have +1.5, -4. And so looking at our graph from left to right, we can see that we are decreasing from -infinity to -1.5. And that is the same thing as saying all x values less than -1.5. Next, we can see that from -1.5 to 0, we are increasing. So we would say we are increasing for all x values between -1.5 and 0. So then one more time, once we reach 0, we have a change in direction. So from 0 to 1.5, we are decreasing. And so for our last interval, we are increasing for any x value greater than 1.5.